Alright, well, welcome back. This is Lecture 8, Part 1 for Engineering 101 2016. Up until this point, we've been talking about the little man computer, but just a little bit of background. There was an error in a very, very early version of Assignment 3, which had the wrong month, but the correct day. So Assignment 2 and 3 were due Monday the 21st of March at midday. Assignments 4 and 5 are due at the 11th of April, again at midday. So up until this point, we've been talking about the little man computer with his basic core components: his addressable memory, where he stores and retrieves information; his calculator, where he does calculations; and the result register, which is the number on the face of the calculator, where he stores important information to transfer it from one place to the other because he can't remember it himself. We have the input and output registers. Those are the only ways of contact with the outside world the little man has, and the program counter for getting him to remember what step through his process he's actually in. So just to review the little man process: he wakes up, goes to his program counter, gets the number from the program counter, goes and retrieves the number from that corresponding address in the addressable memory, then does whatever that number tells him to do, then he increments the program counter, rinse and repeat. So that's what we're talking about so far. We've been talking about load and store commands, and all of this what we're talking about so far is an example of von Neumann architecture, where your memory contains both your data and your instructions for the program, and that's interpreted by the CPU, which is part of the little man computer. So at this moment, I just want to take a step back and discuss where we actually are. So where the little man computer sits is between the level of the machine language and a high-level language. So when I say high-level language, I mean something like Python or C or Java, which is what most of you have been doing in Comp 102. So Java is our high-level language up here, and it has to go through a few steps before that can actually be executed by the little man computer. And in the past, I've wrapped all this up and said, oh, it's the compiler that does that. Yes, that's true, but what your compiler does is it turns your Java code. So let's say we've got a Java statement which is printf, and then it has some string in there. Let's call it the letter T for argument's sake. So before that code can be executed by something like the little man in your CPU, that has to be compiled. So the compile step, that takes your Java code and it turns it into what is called assembly code. Assembly. So assembly code is what we've been talking about as the human readable form of the little man computer. So this is like imp, out, store, and various other commands like that. So the compilation step takes your Java, Python, whatever code it is, and compiles it into assembly code of that type. Now, each different computer architecture has its own unique version of assembly code. Sorry about that. And the step beyond that, which we haven't talked about yet, is the interpretation of that. That gets further converted by something called the assembler, and that is what finally gets turned into executable machine code. Another name for that is opcodes, operational codes, and those are the 901, 902, 513 kind of things that we've been talking about in the last lecture. So these two down here are they both change depending on the hardware that you're on, whereas something like Java, a high-level language, that can be programmed in and compiled on a number of different architecture systems. So a little bit later on in this lecture, I'll show you a specific example of assembly code for x86 architecture, and you can imagine that every different kind of architecture has its own assembly language and its own opcodes below that. If you're interested in more detail in the LMC, here's a more detailed description. So now I want to talk about variables, but before we do that, skipping through ahead, I want you to think about what would happen if we ran this piece of code here. So you can see the assembly code on the left, the machine code on the right. Just have a look at the assembly code on the left, stop the video if you can, and think about what it's going to do. Okay, hopefully you've had a chance to stop the video and think about what that is actually going to do. On the surface it looks pretty simple. On the surface it looks like the program is going to take two different inputs, store one of them at memory address 12, store one of them at memory address 4, add the two together, and then output the sum. Actually, take a closer look at what happens on line 4 of the program. We have the store 4. That means store the second input in memory address number 4. But the strange thing is that we've already got something in memory address number 4. If you look at the listing 2, the machine code on the right hand side, you can see that the 4th line, so the first line is 901, second is 312, 901, 304. The line that says 112, the one that corresponds to add, that is actually where that store 4 command will store whatever value we've given at the second input. So this is an example of a piece of code that will overwrite itself while it is running. So without telling you what that second input is, we can't know what this program is going to do. In actuality, it will probably crash in most cases, but you can write little man computer code to overwrite itself. That's one of the big dangers of von Neumann architecture, because you store both your program and your data in exactly the same place. So in general, in response to this, what we try and do is store our little man computer instructions and little man data as far apart in memory as possible. And the little man computer has been around since about the 1950s, so you might think that we've discovered all there is to know about opcodes in assembly. The weird thing is that in 2014, a bunch of researchers found this thing called row hammering, and this is where you use assembly code, opcodes, to access, read and write from a memory cell adjacent, directly above or directly below the memory address that you're interested in. And it turns out if you access them often enough, because of the physical nature of these memory addresses, which we will come back to in 101, you can edit the value of an adjacent memory cell by changing the ones next to it enough. It's a rare event, it doesn't happen often, but it happens enough and reproducibly enough for this to be a well-documented bug. And this is actually a whole new area of security research, looking at how you can securely separate memory addresses from the addresses adjacent to it. So this piece of code that you can see here, this is assembly code for x86, so this would be interpreted by the assembler and turned into opcodes for x86 architecture. If you want to learn more about row hammering, it is really interesting. We don't have time to go more into it now. Go have a look at it on Wikipedia, and it's just a fascinating new area that you'd think we would have discovered years and years ago, but it's only just becoming apparent how potentially dangerous techniques like this are, and they all involve the use of either assembly language or opcodes. So here's a different question. With our little man computer instructions, can we get our little man to return a number to the output without inputting a number? And actually, with our current set of opcodes, with instructions, with load, store, input, output, hold, we can't do that. We can get him to output the number 0, and that's it, unless we've got access to his memory. And so in response to that, we actually have another new opcode called DAT. And DAT is how we create variables and how we give numbers to our program without using the input command. So on the left hand side here, you can see some assembly code which says LDA A out halt. That loads A, and A is just a variable. That's how you declare to load a variable in opcode. And you can see line 3 of the program is ADAT61. That line there means store the value 61 as variable A. And the weird thing is that the line number where that ADAT61 command is, that gives you the memory address where the value for A will be stored. So let's just go over that again. If you look at the right hand side of the slide, you can see the opcodes for this: 503, 902, 000, and 61. 503 is the equivalent of load A. Why? Because 5 is the load command and 03 is the memory address. So A is actually just a memory address location. In this particular piece of code, it's memory address number 3. Why number 3? Because line 3 is where the ADAT61 command appears. If we had BDAT62, that would be stored at memory address cell number 4 if it was on the bottom of this program, just because that's the line number where that would go. You don't actually need to know where the memory address is for a variable. The lovely thing about your assembler is it reads through a program like this, and it sees a value, a variable like A, and once it's read all the instructions, it goes, okay, I go back through that, and when I'm generating the opcodes, I replace every place where I find the letter A, I replace it with the memory address where A is stored. In this case, 03. And so your program, by declaring variables, you can much more easily give it numbers rather than opcodes, and you can use that to store information. So that's what your DAT command is. DAT stands for data, and what you're really doing is declaring a nice safe place for your program in which to store numbers rather than opcodes. So you're essentially saying line number 3, memory address cell number 3 for this program is a safe place to store the number 61, which I might want to use for my program down the track. So why does DAT come after halt? That's kind of what I've just explained to you, because halt is the final line in our program. So we know everything after that won't have anything to do with our program anymore. We're now into safe memory territory, and we won't accidentally overwrite our program by having a value in there. There we go. So that's it for this part of lecture number 8. That's it for the little man computer. We've got one more short section on the little man computer, which will come in part 2. But have a think about all those questions there. Watch the John Oliver video that I've linked, and just be aware that actual opcodes aren't encoded in these decimal 902 digits. They're usually encoded in either hex or binary. You can look up why as part of the challenge, but we'll stop it there for a moment, and I'll see you in part 2.